So hi everyone. So I'm going to share this session. So let us start our oral presentation. So I'm from University of Salford, UK. So actually it was supposed to chair by Professor Gopadappa. Since he has some urgent meeting, he got an urgent meeting. So he just asked me to replace, asked me to engage this session chair. First paper, of course, you will have a 20 minutes presentation. So last 5 minutes for question and answers. Okay. So yeah, try to maintain the time. So otherwise, last paper, yeah, if the last paper should face in some problem. And of course, at the end, everyone should face problem, face any problem. Okay, if you finish early in time, then we go early. Otherwise, yes. Okay, this is the first paper. So a prototype typical signature approach for writer independent offline signature verification. So it should be presented by
Cassia.
Okay, thank you. So, okay, yeah, just go for it.
Thank you, Professor. My name is Cassia, and today I'm a PhD candidate at École de Technologie ICPR in Montreal, Canada. And today I'm going to present our work on the use of prototypical signatures for write-independent offline signature verification. So let's start with some context here. So in offline signature verification, we rely on static signature images as the one shown here. And the goal is to differentiate between genuine signature and forged ones. The forged signatures can range from a random attempt to high-skill reproduction, which are much harder to detect given similarity to the genuine signature. There are usually two approaches to create a signature verification. The first one is the write independent, where we create a dedicated classifier for each user. This approach usually yields better performance, but it also increases complexity, given it requires individual training data and separate model for every new user. The other approach is the write independent, in which we investigate this work. In this approach, we create a single classifier for our users, which decreases complexity and also enables scalability, scalable implementation, sorry. Usually this approach is implemented by transforming the biometric any class problem to a binary classification problem. And this, for example, is achieved by creating dissimilarities where we use a pair of signatures. So for creating training data, we can compare genuine signatures to form a positive sample and a forgery and a genuine signature to form negative sample. But regardless of the approach used, one problem remains. We don't have skilled forgery during training, and despite of that, the system is expected to detect skilled forgery without ever having learned the characteristics beforehand. So one alternative widely used in the literature is employing random forgery as the negative sample. Random forgery means the genuine signatures of other users. Here in this picture, we illustrate a common write-independent approach for generating training data. So first we have a set of signature images that goes to a feature extraction step. These feature vectors are stored in a database. And here we also illustrate the signature in the feature space. And when we want to generate training samples, what happens is for every user, we select a set of genuine signatures to form the positive samples. And we also select random forgeries for forming the negative samples. The problem here is that this selection of random forgeries are performed arbitrarily without considering any relationship with the genuine signatures. So when we move to the dissimilarity space, this results in negative dissimilarity that with poor location, and because they are dispersed in the feature space. So this limits their usefulness for detecting skilled forgery, which lie much closer to the genuine samples. And this is exactly where our approach comes in. So after extracting the features, we perform what we call data-driven summarization that's going to generate a compact set of prototypical signatures. These prototypical signatures summarize the characteristics of all signatures in the development set. And with this reduced set, we instead of selecting samples randomly, we can do so using a distance metric to the genuine signatures. So in the end, we have negative samples that better approximate to the skewed forgeries as we initially intend to. So this is our proposed method in detail. As I mentioned before, the process starts with a set of signature images that are derived from many different users. These undergo a feature extraction using a previously learned model, and the feature vectors are stored in the development set. Then we apply summarization, and this summarization is going to group all the signatures and key regions, generating key prototypical signatures that are stored in a set C. These signatures serve as candidates to the negative sample selection. The next step we perform for every user. So for every user, we retrieve the signature, the genuine signature feature vectors. Then we compute a local centroid, and local centroid means that is denoted by an average feature vector across all user signatures. And using this local centroid, we then select the closest prototypical signatures. These prototypical samples with the genuine feature vectors form the training sample for that user. And then we apply a dichotomy transformation to transform that in the dissimilarity samples. We do so to all users, and then we get all these dissimilarities combined to train a single classifier. To evaluate our method, we employ three data sets: CDAR, MCYT, and GPDS synthetic, which are databases commonly used in this type of work. We also evaluate different backbones, specifically 7 models across 3 different architectural families: AlexNet, ResNet, and Vision Transformer. And for the verification step, we employ 2 approaches: the SVM with a radio-based function kernel, which is commonly used for signature verification, and also a linear SVM training the primal formulation using optimized with the stochastic gradient descent. We report the performance in terms of the equal error rate, which are reported in terms of average and standard deviation. So following primal work, we segmented the data sets into a development set for training and an exploitation set for testing, using the joint number of users for each set. So to generate the dissimilarities, for each user in the development set, we create a balanced number of dissimilarity samples. So we have a balanced number of negative and positive dissimilarity samples. And we did that for the standard approach, which use random forgery, and our approach, which use prototypical signatures instead. Likewise, we also, for each user in the development, the exploitation set, we select a number of reference signatures. We use a varying number of reference signatures, and this reference set is compared against a claimed set, which comprise genuine or random forgery and skewed forgery. So they create the dissimilarities that are used for testing. For the summarization process, we use a clustering method over all the signatures in the development set. And in our case, we adopt the k-means due to its simplicity, scalability, and also its ability to compute meaningful centroids. In addition, we also measure other aspects of the system, such as the training and test time, the model size, the number of support vectors, and also the number of floating point operations for training and also for testing. So for defining the number, the hyperparameter k, we performed a cross-validation over the development set. We did so using only genuine signatures. We use a disjoint subset of users for training and for validating. And we ranging the k from 10 up to 600 depending on the data set. And the k yielding the lowest error was defined as the optimal values that we use in the subsequent experiments. So here we see the performance with prototypical signatures. Let's look first at the top figure. Here we show an equal error rate as a function of the number of reference signatures. And the performance with our approach, showing with the dashed lines. And as we can see here, it usually returns, in most cases, the lowest error, and regardless of the number of reference signatures. And this is achieved while reducing the development set size. What we can observe in the bottom figure. In this figure, we see the equal error rate versus the number of the number of signatures in the development set. And for example, when you use the standard approach, which is showing with circles, if we look at the first chart for the PBS synthetic, for example, we see that in the development set we have almost 14,000 signatures, and our approach downsized that to only 100 for the linear SVM or 150 for the SVM RBF. So this is also achieved for the other data set. And we also compare the SVM RBF and the linear SVM optimized via SGD under identical settings on the GPDS synthetic. In this figure, we can observe the curves evolving as the number of users in the data set grow. And what we can see here is that the difference is substantial. So we see that the SVM RBF increase steeply regardless of the metric being measured, while the linear SVM is almost constant. In the table, we show the results when we use the largest number of users for training and for testing. And what we achieved here is that when using prototypical signatures with the linear SVM, we got 150 times faster system at training, almost 4,000 times faster at inference, and almost 18 million times fewer floating point operations for inference. So this altogether unlocks scalable implementations, so we can implement real-world application that has millions of users, for example. We also compare the SVM RBF using the standard approach and our approach using the linear SVM under different backbones. Here in this table, we show the equal error rate and user-specific thresholds, and we highlighted the results that report statistical equivalence. And as we can observe also here, in almost case, in almost backbones and dataset, we got statistical equivalent results, even using a linear SVM, which is faster. So this means that our system works independently of the model being used for structuring features. So to conclude, I can summarize our main contributions in 3 points. So first, by using the prototypical signatures, we generate more informative negative samples, which means that they provide, they better approximate the characteristics of skilled forgery in returning improved performance. By using our method with a linear SVM optimized via SGD, we enable the development of more scalable solutions. And it's backbone agnostic, so it can be integrated to existing systems For future work, we plan to explore alternative clustering methods for the WI implementation, and also extend the work to adaptive learning of prototypical signatures. These are some links and contact address for those of you who would like to know more about work, and that's all. Thank you very much for your attention.
Now that's the time for questions. We have 5 minutes time. Yeah, please. Go ahead.
Hi, thanks for the talk. So you had the signature features in some kind of embedding space earlier. I was just wondering how you set the threshold that goes from genuine signature to skilled forgery and then to, I guess, random.
I'm not sure if I completely understand your question, but in our case, we use pre-trained models. So what we have is the features already structured. So we are working all the time on the feature vectors. And for creating the samples that's going to be used for training, we transform that into similarities. So we are not learning the representation for that.
Okay, so you perturb the genuine ones to get skilled forgery.
The data sets, they are already comprised of some forgeries, the skilled forgeries. In that one, we use for testing only. That's so the data set already have some testing samples, so we can measure, and this is what the work in the literature do in that case. So every data set already have a set of.
Okay.
We don't
I thought
create.
you were making your own or assigning them. Yeah.
Yeah, I don't create the signatures for testing. They are already there. I just evaluate if we can detect that very well. So that's basically.
Thank you.
So, any other questions? One more question? If not, just I have a simple question. So, when you are comparing signatures, see if you miss some information in the signature, that means the input image, what happens?
So in this case, we are working to generalize to all users, right?
Okay, yeah.
So it's like we have a system. So we are going to ask you, for example, you are a user, and you are going to access that system. So you have to write your signature.
Yeah.
Then it goes to all the process.
Yeah.
And we have some signatures there that say, okay, this is the original signatures of that user. Okay?
But when you are writing, if you miss.
So probably this is going to return a false positive for the forgery one. And maybe you have to retry that.
No, why I'm asking this question, probably is it possible to restore the missing information?
No, because in this case, it's like we have to be sure that's you that's accessing the system, right? So you should write your name properly.
Yeah, in case because of pen or something, probably.
Yeah, maybe the pen or if they don't match. What we usually do, for example, for creating some, for signing some important papers like for bank, creating bank accounts, we sign our names multiple times, right? Because we have the interface for everything. So it's kind of solved that problem.
Yeah, that's what, yeah.
Yes.
We can go for a multiple signatures of the same person. We can
Exactly.
use it. So that's the one. Any other simple question? One big question. So did you think of security perspective? Signature is some kind of privacy.
Yes.
Probably, yeah.
You raised that point. In our case, one of the important things about using prototypical signatures is that once that you summarize, we don't have the real signatures anymore. So what we store.
That's nice. Yeah.
Yes, exactly.
So yeah, thank you very much. Just again, guys, thank you. It was well presentation.